The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today, the idea is to think about CT systems in exactly the same way that we thought about DT systems last time. For the past couple weeks, we've been looking at many representations of both CT and DT systems. Last lecture, we made a picture of a bunch of different ways to think about DT systems, and we tried to think about relations between them. The new thing from last time was this idea of a Z transform, which formally is the link between a system function, a function of Z, and a unit sample response, a function of n. We showed last time that because we already understand a whole lot of these other connections, that connection is very straightforward. What we're going to do today is precisely the same thing for CT. The boxes barely changed. You should see the relationship immediately between the former set of boxes and this set of boxes. And we'll do a very similar thing. We'll look at a relationship between the system function, which is a function of S, and the impulse response, which is a function of t. We'll look at that similar function for CT, the thing that's analogous to the Z transform in DT. So Laplace transform, just like in DT, where it maps a function of time to a function of Z, here it maps a function of time, which in CT we'll write that way. It maps that to a function of S. So S is going to be something like x of t e to the minus st dt. So the idea is going to be that this was a function of time. This is only a function of s. We get the function of s by integrating some function of time, but we integrate time out, so time disappears. So the idea then is that we end up with a map linking a function of time to a function of s. Presumably you've seen this before. This is a topic in 1803. Smile. Nod your head, make me feel like I'm connecting to you, right? So you've all seen this before, nothing's new. Actually, there is one tiny thing that's new. In 1803, they use a variant of the Laplace transform that we will call the unilateral Laplace transform, which means they started their integrals at 0. For reasons that will be clear at the very end of the course when we do Fourier transforms, to make the transition between this kind of a transform and a Fourier transform easier, we will do something called a bilateral transform. The only difference being that we will start our integrals at minus infinity. There are subtle differences between those two transforms. Rest assured that the big picture is identical. And when there is an important difference, we'll point that out. So for the rest of today and for the rest of 2 weeks, I will only talk about bilateral transforms, the kind that we integrate over all of time. And the easiest way I know to get started is to just try some, right? You could study properties of the math. That's probably the way it was studied in 1803. I find it easier to develop some intuition for what's going on here by just doing some. So here's probably the simplest Laplace transform we'll look at. What's the Laplace transform of a function of time that exponentially decays with positive time and is 0 for time less than 0? As you might expect, the first transform we'll do involves simply plugging that mathematical formula into the definition. So the x of s, the Laplace transform, is always the function of time integrated against e to the minus st. We're only doing bilateral, but notice that the 0 for t less than 0 cuts off the bottom. So in fact, you would get the same answer if you did bilateral or unilateral. And then we're left with integrating an infinite, running this integral over infinite time of this kind of a function, which comes out looking like this. The only tricky thing is thinking about the implications of that infinity thing. There's going to be certain values of s for which that integral diverges. So to think about that, think about the thing that we're integrating. We're integrating something that looks like, say, e to the pt. We're integrating against some function. So the original function of time is e to the minus t. Here we have e to the minus st. Let's just focus on that one for a moment, the e to the st thing. We're going to generally be worried about values of s, or here values of p, that have complex values. We're going to be looking at the s-plane, just the same as last time we looked at the z-plane. So we're going to think about this thing might have a real and imaginary component. So we might have something that looks like this. Sigma would be the real part of p. Omega would be the imaginary part of p. And somebody want to hazard a guess at what that might look like as if I tried to expand it as a real and imaginary part? Someone want to hazard a guess at the name of the equation I might use? Euler's equation, sure. So I would expand this by Euler's equation, and I get something of the form e to the sigma t cos omega t plus j sine omega t. The point of writing that out is that I hope it's clear that convergence of the integral is going to depend critically on the real or the imaginary part. Real, right? So the convergence is going to be determined by this. This is the thing that's affecting the magnitude. That's the thing that's getting smaller or bigger as I go to infinity or minus infinity. The cosine term, the sine term, those are oscillating. They don't make the function be more or less convergent than it was originally. So when I'm thinking about convergence, I'm going to be thinking about the real part. So over here, if I want to make convergent than it was originally. So when I'm thinking about convergence, I'm going to be thinking about the real part. So over here, if I want to make